You've seen the graph of y equals x squared before. It's called a parabola, a kind of symmetric U-shaped curve. Here are two more examples of parabolas, and you might think that, hey, they all look kind of similar. So you might guess that perhaps they're all related to y equals x squared in a simple way. Each of these parabolas comes from what's called a quadratic function, a function of the form y equals ax squared plus bx plus c for some constants a, b, and c, with the one condition that a is not equal to 0, otherwise we would just have a straight line. So our goal is to find out the connection between the simplest quadratic, y equals x squared, and any general quadratic. Well, let's look at these two parabolas. For the green parabola, it's as if we took y equals x squared, flipped it upside down, and then shifted it left and down. For the red one, it's a bit narrower, as if we stretched y equals x squared vertically and then shifted it right and up. So really, what we've done in both cases is just a combination of the following geometric transformations. Firstly, there's a scaling, which is stretching or compressing the parabola vertically, and possibly flipping as well, which is reflecting the curve across the x-axis. And secondly, shifting, which is moving the entire parabola to a new location. So it looks like any quadratic function can be obtained from y equals x squared through some combination of a scale, a flip, and a shift. Let's show that using algebra. So the expression y equals a times x minus x0 squared plus y0 is called the vertex form of the parabola. And we'll see why it's called that. And basically, it's just expressing what we just said, except in symbols and algebra. So let's see why this expression correctly encodes a combination of scaling, flipping, and shifting. So why does this formula make sense? Let's start with the graph of y equals x squared. And now, if we look at the order of operations in the expression, we first need to square the x minus x0 in parentheses, which has the effect of moving the parabola horizontally to x0. And why is it x minus x0 and not x plus x0? Well, one way to think about it is that plugging in x0 for x should give us 0, since the height of this red curve at x0 is 0. And so we should do a subtraction. Next, we multiply by the scale factor a. For example, a equals 2, which will multiply every value by 2, and so the whole curve gets stretched by a factor of 2. If a is negative, it would also flip the curve about the x-axis. Finally, we add the constant y0, which shifts the whole curve up if y0 is positive and down if y0 is negative. Okay, so that's what it means to apply the geometric transformations of scaling, flipping, and shifting the original parabola y equals x squared. Now, our goal is to show that any quadratic can be written in this vertex form, because that would then tell us that any quadratic is just a combination of applying those geometric transformations to y equals x squared. So we'll start with the general quadratic, y equals ax squared plus bx plus c, which is called the standard form of the quadratic. And we want to transform it into the vertex form up there. Well, notice that in the vertex form, there's a perfect square term, the x minus x0 squared, and then a constant term, y0 on the outside. Well, this is exactly where completing the square comes in. Let's try to apply it and see. First, we factor in a out of the first two terms, which would give us x squared plus b over a times x in parentheses. And then we take that and apply the formula for completing the square, which gives us this. That's the formula for completing the square, which you can see is true by expanding out the terms on the right-hand side. Basically, completing the square lets us rewrite a quadratic so that one part of it is a perfect square and the rest is just a constant. By doing this, it will allow us to see some properties of the parabola more easily. Now we can distribute the a, and it looks like we are basically done. If we just rearrange things a little bit, this is what it looks like. Our scale factor is a, our x0 term is negative b over 2a, and our y0 term is c minus b squared over 4a, which is exactly the vertex form that we wanted to write it in. So we did it. We showed, using algebra, that any quadratic is just some combination of scaling, flipping, and shifting the simplest quadratic, y equals x squared. Now, to tie everything together, let's interpret these three constants that we got, the a, x0, and y0, and see how it connects with some formulas you may have seen before. So again, this is the vertex form that we got, and it scales y equals x squared by a factor of a and shifts it to a new minimum point called the vertex of the parabola. That's why we call it the vertex form of the parabola, because it directly reveals the numbers x0 and y0, the coordinates of the vertex. The x-coordinate, which determines the horizontal shift, is negative b over 2a, and the y-coordinate of the vertex, which determines the vertical shift, is c minus b squared over 4a. So in the picture here, the scale factor of the yellow parabola is a positive number a, meaning we stretched it but didn't flip it upside down. And from the picture, we can see that the curve will intersect the x-axis when the vertical shift is less than or equal to 0. In other words, we will have a root of the quadratic equation. And if we rearrange terms in this inequality, we see that it's equivalent to b squared minus 4ac being greater than or equal to 0. The term b squared minus 4ac is called the discriminant, which is the term under the square root in the famous, or perhaps infamous, quadratic formula. You may recall that a quadratic equation has at least one root exactly when the discriminant is greater than or equal to 0. Similarly, if the vertical shift is positive, then our parabola won't intersect the x-axis, which corresponds with the discriminant being negative and there being no roots. The case when a is a negative number is similar, except with all the inequalities flipped around. Now, in fact, we can actually derive the quadratic formula from our expression for vertex form. To do that, let's set our expression equal to 0, and then solve for x, which will give us the roots of the quadratic. First, we move the constant to the left and rewrite it as b squared minus 4ac over 4a. Then we divide throughout by a, take the square root of both sides, and then subtract b over 2a from both sides, which finally simplifies to to the quadratic formula.